collector would buy both.
Yeah, you get both of them so that you could have both of them.
Okay.
I think that's the main
Don't you
thing.
pay all the money too?
Of course you pay that bit of money. All right, so today I was just going to do a review, and the review of that the form that's going to take is we're going to collaborate here and create a binary search tree in Python. In the next 50 minutes, we'll add as many features as we can fit into those 50 minutes. All right. So as a review here, remember that binary search trees are trees. Yeah, go ahead.
So for the homework, we only need to make test cases for the error.
Right. Yeah. No test cases for the RSA stuff. Right. Exactly. Remember that trees are acyclic graphs. Binary search trees are oriented down in order to hold data because we read top to bottom, left to right. Each node in a binary search tree contains a unique key element, right? And we're just going to stick with integers for now. The root is at the top. Nodes have children, a left child, a right child, or they could maybe have one or the other or neither, right? If they have neither, then they're called a leaf, right? We have the binary search tree property that if I have a key k, then the left subchild is less than k, the right subchild is greater than k, if they exist. So for that, if we do not allow duplicates, basically, we're going to require that all keys are unique. Okay. To search for the node, you start at the root. You compare keys left and right as you go down the tree. If we need to, we can go ahead and create say an unbalanced example here. There's a binary search tree, right? There's 15, and then everything in the left subtree here is less than 15. Everything over here is greater than 15. So if I search for, say, 7, wow, good. What am I going to do? I'm going to start at the root. 7 is less than 15, so I go left. 7 is greater than 6, so I go right, and I find what I'm looking for. Right? And this sped up a little bit here. We'll find what you're looking for. Sometimes a search does not end in a success. For example, if you search for 8 here, you're going to start at 15, 7, and go to eventually to 7, and find that it has no right child, so therefore you end with an unsuccessful search. How do we end up inserting something? Let's insert that thing that we didn't see, we didn't find, 8. Well, it's the same exact process as searching, and when you find that it doesn't exist, you go ahead and insert it there. Okay? So I want to start purely from scratch here and start designing and implementing our own binary search tree. So help me out. Of course, in Python, we would have a class, right? Def class. What should we call it? Binary search tree, because that's what it is, right? And is that the correct syntax? No, there's no. It's not a function. There we go. And there's no def, is there? It's just a class, right? All right. So in Python, if you create a class, the constructor, there's only one constructor in Python, and it's this magic function called init. Right? And you always have to make sure that you're passing in self. That's like this keyword in Java, and so I've got self. Right? How do I initialize this? If I create a tree, I want an empty binary search tree. So self.root is equal to none. This is an empty binary search tree. We could also keep track of other things. For example, size. Right? Self.size is equal to 0 if we want to start with an empty tree. It's not like a programming language like Java where you need to declare this stuff, right? There's going to be this root right here, and it's a node that contains a key, left child, right child, whatever. Once you set, there is no private, there's no public in Python. Everything is just public, right? By convention, if you want private variables, I think that the convention is to do something like this: begin with an underscore, and then this is foo ends up being a private variable. I mean, you could still access it publicly. You just don't do so because it begins with an underscore. All right, there's our binary search tree. But well, what is the root? The root is a node, right? It's a node that contains a key and also a reference to its left child and a right child. So that tells me I probably want another class, right? To represent a node. We also want a constructor there, initialization, init, self. And by the way, if you don't include self, what have you done? Inside the function, you won't be able to refer to the object that it was called on. You can still do this, but then it becomes essentially static, right? Self. Yeah.
So when you put an underscore in front of it, can you still call it as it?
Yes, you can. I mean, it's not going to be. It's not actually going to be private or protected.
Okay. Just write it like that.
Yep. Self.key. Well, if I'm going to create a node, I'm probably going to want to create a node with at least a key in it. So just remember that the first argument always has to be self to any member function, member method in a class. This key here will then be set to key. There we go. What else do I need? Oops. What else do I need in a binary search tree node? A reference to a left child, a reference to a right child, at least. So by default, we'll just say that the left is equal to null. Yeah, but you can't do that in Python. None is the keyword there, right? Self.right is equal to none. And if you want to have your tree be more flexible, you probably also should keep track of the parent. None. There we go. All right. So I've now created a shell of a program here. Eventually, I'm going to want to print out the contents of a node. So here's another magic function. Magic functions begin with underscore underscore, right? str, that's basically the toString function in Java. Right? Everybody already knows this stuff? Yes? No? In Python? No? Okay. All right. Then it is worth it to mention this kind of stuff, I guess. All I'm going to do is return self.key, right? And you know what? I'm also going to wrap that up in a string because I know that I'm going to be storing integers. And if I want a string representation of an integer, I want to immediately cast it to a string so that you can, you know, treat it as a string and print it out. Okay? Uh-oh. What's wrong? I don't know why it's... is there something wrong there? I don't know. We'll find out if I try to run it. CSCE 310, Python trees. There we go. Self. That should be right. Isn't it string? Self. Init. Are these not... This is all indented. This is indented. Huh. Maybe it doesn't like that vertical white space. Class node. Oh, duh. Well, no, this is fine too. This should be fine. Self key, self none none none. Self key. Anybody see what's wrong? Invalid syntax. Init. Node. Oh, duh. What am I doing? So when you define a function, what does it look like? Def. Yeah, you do need def all over the place here. Right. Python is not my native language. Right. So there we go. Okay, that should be fine. Yeah, I mean, I knew something was wrong there because, of course, it was syntax highlighting. It was blanking the rest of that stuff out. All right, that's good. I can create a tree now. Tree. I don't know. T is equal to binary search tree. Search tree. And I can, you know, the constructor here doesn't take any other arguments. Implicitly, it takes itself so that it can initialize itself, its values here. But there, that's it. All right. Now, there's not much to do with this tree unless you can put stuff into it, right? So let's go ahead and insert 50. To do that, we need to implement that function. Okay. So def, insert, self, and then the key that we want to insert here. Now we need to take care of an edge case first of all. What happens when you insert into an empty tree? What happens when it becomes the root, right? So if I create an empty tree here and I insert, say, 50, then it simply just creates a brand new root node. So if self.root is none, that's probably the more Pythonic way of doing it. You can do equals equals, but is none is probably the preferred way of doing it, right? If self.root is none, then self.root becomes a new node with the value of the key. Right? And also, what else should we do if we're keeping track of the size? Self.size plus plus, but we can't do that, is equal to self.size plus 1. But we can do this, plus equals 1. Why they would take out plus, or never add in plus plus, but allow you to do compound assignment operators is beyond me. Right? Okay. Well, if I do that, then now I can actually do something with it, right? Let's go ahead and print t. What's it going to print right now? In Java, if you don't define the toString method, what does it print? The memory location. Kind of does the same thing here. The memory location of this binary tree object. Okay. So we probably want to also define a toString function essentially here, right? Where for now, let's just go ahead and print the root. Print return a string. Root is plus self.root. There we go. Oops. Concatenate string. Can only concatenate string. Fine. I'll go ahead and surround that with the string, which will then implicitly call the string function up here. It should at least. Yeah. Root is 50. Right. There we go. That takes care of the corner case where we can actually get one thing in there. But now, if it's not empty, what do we need? Oh, and then I'll return here. Otherwise, I'll continue. All right. Now, how am I going to get something in there after I've already gotten one thing in there? Let's go ahead and create an unbalanced example here. Oh, it's the same one as before. If I insert 8 here, what's the first step to actually inserting something? Find it, right? And so you can write another routine to find the node at which it exists. You don't really want to do that though, right? If it exists, then immediately stop because you don't want duplicates in your tree, right? So we'll go ahead and implement this find along with the insert all in one in the same method here. Now, to do that, what I'm going to do is I'm going to keep track of two things. I'm going to keep track of the previous node and then the current node, because once I travel down the tree, here initially I'm at the root, right, for the current, and the previous is nothing. Then I go down to 6 over here. 15 follows this. Then go down to 7. 6 follows this. Then I go down to none. That's where it should be inserted if it needs to be inserted. I am keeping track of both of these things so that I have the old node, the previous node, so that I can actually insert it with the previous node. Otherwise, if I fall off the edge of the tree here, right? If I want to insert 9 now, right? And I fall off the edge of the tree, I lose my reference for what I need to insert. Okay? So let's keep track of a previous. Initially, that's going to be none. And a current node, which is going to be self.root. We start at the root. Okay. Now I'm going to traverse down the tree until the current node has fallen off the edge of the tree. So while current is not none. Right? That's the Pythonic way of doing it, I believe, right? I've kind of the proto version that I did before used the not equals. You can use either one, right? Is not or is not equal to is not. I think that that's the preferred way. Yes? No? No hardcore Pythoners here? All right. The Pythonic way of doing things would be that way. All right. All right. So to traverse, I've got the current and I've got the previous. Right. Where is the previous? What's the previous going to be updated to? The current. So previous ends up being the current. Now I need to update the current. I need to either go left or I need to go right. Which way do I go? If the key is less than the current node's key, then the thing that I'm searching for is in the left subtree, right? Go left. So current is equal to current.left, which might be none if it has no child, but that's okay because that's when we break out of this while loop here, right? Otherwise, else if the key is greater, current.key is the key is greater than that, then, oops, go right, right? Yeah, go ahead. Well, there is no next here. I'm looking at the current, right? If that's 15, we'll get to what happens when they're equal here in a second. But 15, I'm searching for 9, right? I need to go either left or right. Well, in this case, I would look at 15 and I'd say the thing I'm searching for is 9. I need to go left. Right? So the current node gets updated to this one right here. Right? It could be that you rename your variables to current and next. What I've done, though, is previous and current. So we're just off by 1. It would be the same thing. Right? All right, I'm going to go right here. Otherwise, what's another possibility here? What's the only other possibility? They're equal, right? Equal. So if 9 is already in this tree, what do we do? What happens in this version if I insert, say, 8 a second time? No duplicate vertex allowed. I like that. I'm going to keep that. If they're equal, already exists, I'm just going to simply return, right? Jump out of this entire thing. That we're going to end up not changing the tree at all. We're not going to allow duplicate values. Okay. All right. Now that I'm out of this loop, right? Previous points to the parent, right? Current is none, right? You need to insert where current is, right? And I'm putting that in the quotes there because obviously it's nothing. It's nowhere. So let's go ahead and create a node. U, right, is equal to node with the key that you want to insert. Right. Now I need to know whether or not to make that the left child or the right child of previous, right? Make U into a child of previous, or prev, right? How do I know if it goes left or right? Well, I just need to make another comparison. If the key is less than the previous, then, make it into a left child. How do I do that? Previous.left is equal to U. Otherwise, else if the previous dot key, there we go. If the previous dot key is less than the key, then make it into a right child. Previous.right is equal to U. Now, do I have to check to see whether or not they're equal? If they were equal, I would have already returned from this function. So no. So I don't actually even need an else if here, do I? I'll just go with else. There we go. What else do I need to set, though? So previous, it now points to, as a left child, this new node U, or a right child, this new node U. But what about U from the perspective of U? What about use parent? That will end up being previous. All right. Okay. Yeah, keep working. All right. Let's insert 25 and let's insert 75. What should it look like? Let's go over here and create a new empty tree here and insert 50. Insert 25. Insert 75. It should look like this nice tree here. Right? When I go to print it though, what am I going to get? Oh, the root is just 50. Right? I could, of course, print the left and the right child, but if I'm going to add a whole bunch of things, I want a way that I can actually, print all of this out. So, suggestions. As a list, okay. So instead of just printing out the root, generate a list of the keys in this tree. ... How? So in other words, say 25, 50, 75. What kind of tree traversal algorithm is that? Left, then root, then right. That's known as an in-order traversal. Why is it called in order? Because binary search tree, it's in order, right? Another way of doing this would have been a pre-order traversal. Another way of doing this would have been a post-order traversal or a BFS, right? So let's come over here and let's do a recursive version first because that's really the easiest, right? So what I'm going to do is I'm going to create another function here, def print in order, right, and self. There we go. Right. And what I'm going to do is instead of returning this, I'm just going to return an empty string here, and I'm going to end up calling print in order because I want to think about this, think about how this would actually work. Don't quote me on this, but I think that you need self.print in order. Is that right? We'll find out. Here, I can test it really quick. Print hello. There we go. So this should print out hello and then return nothing. Okay, there we go. It works. Do I have to do that, though? That's my question. Or is it understood that the scope of that is the self? Nope, you have to do that. So there, now you can quote me on it because now we know the truth. You do have to have self in order to invoke a function on that object. All right. So what do I do? Let's make this recursive. How could I make it recursive? By taking a node, right? A current node. So instead of this dot print in order, I'll also pass in the root node. Right? So an in-order traversal here would say, instead of printing out the current node immediately, it would go to the left subchild, do everything down there, then come back to the root, process that, and then go onto everything in the left subtree. Right? So this dot, or not this, self dot print in order, right? Current dot left, and self dot print in order current dot right. And between those two things, we will go ahead and print current dot key. There we go. Now you do have to be careful here because what if there is no left child? What if there's no right child? We'll be passing in none, which ends up being none type attribute has no left. Right? So with anything that's recursive, I need a base case here where I don't do anything, I just immediately return. If you give me an invalid node, a node that doesn't exist, I will simply just return without doing anything. Okay? So now if this is successful, an in-order traversal of a tree in which I've inserted 50, 25, and 75 should look like 25, 50, 75. Right? Now that is doing it recursively using it's using recursion, but it's also just printing stuff out instead of returning an actual list, which is what you suggested that we do. What can we do in order to get that kind of behavior? Okay, so we can pass in a list, right, along with that. And if it's none, then we don't do anything. And otherwise, we do the left child along with the list, and a right child along with the list. Can I use list, or is that a reserved word? I don't know. I can use it? Okay. And instead of printing it out, what I'll do is I will list.append current.key. There we go. Now, what I'm doing is I'm passing this in to the function. Is this going to work? Now, this is a Python question here, right? So self.string list is equal to self. I'm not going to call this print in order anymore. I'm just going to call it in order traversal, or in order. There we go. Because you're not printing it anymore. And I'll return a stringized version of the list. I don't think this is going to work. Why? Missing one required argument. Oh, okay. What's a new list? How do I do a new list? Just this? Will that work? All right. There. None. So what's wrong? What's wrong is how Python does lists and passing by reference or passing by value. Def, foo, that takes a list, right? List.append 20. Print list. Okay. Now let's create a list here. A is equal to 1, 2, 3. There we go. And then print A, call foo on A, and print A again. So after all that tree stuff, what's it going to print? This first one should print 1, 2, 3. Then we pass it by value, by reference, I don't know. In any case, we receive 1, 2, 3 here, and we append 20 to it. So I imagine that this would print 1, 2, 3, 20. The question about whether or not it's passed by reference or value will be answered with this print statement. Will it print 1, 2, 3, indicating that it was actually passed by value, a copy of the list was passed, or will it print 1, 2, 3, 20, indicating that it was passed by reference, so that changes to the list in a function are reflected in the calling function? Which one is which? How many vote for 1, 2, 3? And how many vote for 1, 2, 3, 20? 1, 2, 3? 1, 2, 3, okay. Oh, it's 1, 2, 3, 20. All right. So it was being passed by reference, right? And changes are reflected. All right. So that means that when we pass in this list right here, right, it should that any changes to it when we make a recursion should be reflected. So let's jump into this. If none, return. Oh, that's why. What's it returning? Nothing. Well, that's okay. Oh, I know what I'm doing. Okay. I need to preserve that in a variable. It doesn't return anything. I give it the list. It changes that list. Great. And then now, once I've got that list, I can stringify it, and there. Now we've got it. If you want to, you can go ahead and change this so that it actually returns a list. But that would be a non-recursive version. And I don't want to do that with only 20 minutes left. How would you do that? You would go back to Computer Science 2 and look up the basic data structure for using in-order, post-order, pre-order traversals. A stack right? That's really easy to do when you're talking about a pre-order traversal, because it's just put stuff into the stack, pop stuff out. Put stuff in, pop stuff out. You just have to do it in the correct order. But in in-order traversal, you need to be careful because you need to know, all right, is this the first time I've seen this node, in which case I want to ignore it and save it for later, and then go to the left child and process all that stuff? Or I'm returning from the left subchild here, and I now need to process this node before going on to the right child, right? For that, you need to keep track of some additional information, and it's a little bit more complicated because it's not just put stuff in, take stuff out. It is check to see, is this the first time I've seen it or the second time I've seen it? And for a post-order traversal, it's even more complicated because is this the first time I see it, need to go left, or the second time I've seen it, need to go right, or the third time that I've seen it, in which case I process it. Right? This is good enough for us right now, at least to verify that it actually works. So how would you go about testing this now? Let's insert a bunch of random stuff. For I in range of 10, right? Insert, or t.insert, random.randint. There we go. For that, do I need to bring in random? Yep. Import random. There we go. So I'm going to randomly insert 10 integers here and print them out. And if it works, I'm convinced that that our implementation here is sound. Oh, that's right. Randint between 0 and 100, exclusive. Right. Ooh, cool. Maybe it was just chance though. Run it again, and again, and again, and again. All right, I'm convinced that it works. Right. What else would we want here? In the last 18 minutes here, do you want to do a generic search, which is basically what we just did, but insert, delete, pre-order traversal, post-order traversal, or a breadth first search? What do we want to do? Nothing? Insert? Well, we just did insert. We're done. All right. Delete. All right. For that, let me first define search. Right? And in fact, let's define search for node. In other words, I want to return a node from this search so that you can have access to its parent, left child, right child, if you need it. All right? So what I'm going to do here is self and then key. So this is going to searches and returns the node which contains key. Returns none if no such element. There we go. In fact, we could probably reuse this here and really clean up this function, right? If we really wanted to. I won't do that, I'll let you do that, but it's basically the same thing as this right here. I'm going to steal that code right here and set up the previous and the current. Start the current at root. While the current is not none, I will go ahead and find, actually I don't need a previous now, right? I'll start at the root, and while that's not none, if the key is less, here, let's change this order here. If the key is equal to the current key, then return current. There we go. Else if it's less, then you need to go left. Else, you need to go right. That's all I need. Now, if I break out of this while loop, that means I've fallen off the edge of the tree without finding the node containing key, and I'll return none. All right. Now, I put in an underscore at the beginning of this because if I were doing this in Java, I would want to make this into a private method. I don't want to have a leaky, what's called a leaky abstraction, right? If anybody could take this binary search tree and then rip out the individual nodes from it, right, then they could screw up the internal structure of the tree. And so technically I would want to make this private. And I've used the convention here of using an underscore to indicate you shouldn't be calling this directly. Right? Call something else. Call, say, for example, def search. Search, self, and key. Right? And what this will do is this will returns true if this tree contains the given key, false otherwise. I want to know if it's in there or not. So all I have to do is call this function. Right? Node is equal to search for this node, and I pass in the key. Right? And if node is none, return false. It's capital F, right? Else, return true. Now I could make that a little bit shorter. How? Return node is none. There we go. If it's none, oh, is not none. There we go. If it's not none, then it exists, and so it's true, and you return, yes, it does in fact exist. Let me go ahead and, after we've filled it up with random garbage, let's go ahead and go with t dot add or insert 50, and then print t dot search for 50. That should output true because it's definitely in there. Oops. Line 52. What was wrong? Oh, it's not a condition that I check. It's just else. There we go. Now what? Search for node not defined. Search for node. Oh, thank you. Self dot, right? There we go. All right, it's true because it's in there. It's right there. Now we could search for something else that is unlikely to be in there. Well, here, 150. Since I'm only filling it with random integers between 0 and 100, that should definitely be false, right? So some ad hoc testing here. I'm pretty sure that this is working. Now 13 minutes left. What did we want to do? We wanted to delete. Why did I do this function first? This search for node is because if you want to delete something, you want to find it first. Okay? So let's go ahead and go with def delete self and key. Right? And let's go ahead and search for that node containing key, not making the same mistake twice here. U is equal to self dot search for node. If U is none, then return. You tried to delete something that didn't exist, so we're done. That's it. Right? Now, at least let's outline our solution here. We want to delete U. Dot, dot, dot. Here's where the review comes in. Let's go ahead and create a random unbalanced example. There we go. So if I want to delete 7 here, is there a problem? Nope. If it's a leaf, then what could I do? Just delete it. Make sure that the parent it's pruned, and that the parents, either left child or right child, whichever the case is, then points to none. Right? What if I wanted to delete 4 here? Yeah, it only has 1 child, so what do? I promote that child up. There could be an entire tree hanging off of this child right here, and it'd be perfectly fine to move that up. But what if I wanted to delete, say, 15 here? Can I promote one or the other of its children? Not in this case. All right? In this case, then that would end up being, I guess I could technically here 23. Let's insert 21. There we go. There. Can I promote one of its children? No, because then it would necessarily have 3 children. If I promoted 6 up, then 6 would have 4, 7, and then 23. as its children. If I promoted 23 up, then that means that I would have 21, 71, and 7 all as children. So what do I do? Do we remember? Look at all these nodes over here in the left subtree. Is there one that I could bring up to the root node here that would not affect the binary search tree property? 7. Why? Because everything else here is still less than 7. Right? What about everything over here? Is there something over here that I could promote up to the root that would that would make everything over here still greater than it? 21. So what's the pattern there? If I go to the left subtree, the thing that I can promote is the maximum element. If I go to the right subtree, the thing that I could promote is the minimum element. In either case, you're guaranteed that there's at most one child, right? Why? What if there are both children? A, B, C. Is A the minimum or the maximum? Nope. This is greater, this is less. So you're not at the minimum or maximum. So outline here. If a leaf, just delete it. If only one child, then promote the child. If both children, find the min or max in the right/left subtree and promote it. Delete its node. And we know how to do that because it's either going to be a leaf or it's only going to have one child. Okay? We're not going to have time to do all of this, and then we're going to move on Monday. So let's just do one condition and maybe another function here. How do I tell if it's a leaf? If u dot left is none and u dot right is none, then just delete it. U dot parent is equal to, or not, u dot parent dot left is equal to none. Or it could be the right child, right? So question, am I a left child or a right child? Lots of questions here, right? These are all node related though, right? A node is a leaf. A node is a left child. A node is a right child, right? That sounds like stuff that belongs in this class up here. Right? So, how do I tell if a node is a leaf? Def is leaf. Return self, say a leaf. A leaf is something with no children because it's a tree, right? So 5 is a leaf, 7, 21, and 50 are all leaves. But 71 has at least one child, so it's an inner node. And this one has both of its children, so it's an inner node. So a leaf is something where the left is none, and self dot right is none. There we go. And am I a left child or a right child? I am a left child. Don't write it like that. Is left child? Self. And is right child? There we go. So that's from the perspective of my parent. If self.parent is equal dot left is equal to me, then I'm a left child. So return this. This is not going to work, and we'll understand why here in a second. Otherwise, I'm a right child if my parent's right child is me. Right? So that goes. I quote it every year. Right? What's the old brain teaser? The Brothers and sisters, I have none, but this man's father is my father's son. Who am I? Who is it? It's me, right? So me, brothers and sisters, I have none. I'm an only child. But this man's father is my father's son. Who am I? I'm me, right? So is my parents' left child me, or is my parents' right child me, right? Tell me about overloading that equals there. Is that going to work? I'm asking you as Pythoners. It might. I mean, I would expect it to work. Let's find out.
Looks like it.
Right? If it's a leaf, so if u dot is leaf, yeah, like that, right? Then if u dot is right child, then I will set u dot parent dot right to be none. Else, if u dot is left child, then I will set u dot parent dot left to be none. What? Aleph, thank you. Is it possible that I'm not neither one?
No.
Careful.
If you're not a binary group,
So I'm not a left child, I'm not a right child because I have no parent.
okay.
I'm a root, right? So let's add another one. If is root, return self dot parent is none. If it's none, then I am a root, right? There we go. And down here, delete, we'll add another condition here. If u dot is root, then what do? The tree root ends up being none. Right. Elif. Oh, and then return. I'm just going to return. I don't want a bunch of elifs. Return. There we go. And return. So if I take care of that root situation, I think I can just do else here. There we go. We can try this really easily, really quickly, with only 2 minutes to go here, by say print t. T returns a what? Is that was that public? The in order traversal? Okay, let's go ahead and get that list. So nodes is equal to t dot in order. And what I'm going to do is I'm going to go t dot delete. I'm guaranteed that that minimum, right, that first one, that's going to be a leaf. Right? So delete whatever nodes of 0 is. There we go. Make sure that we print it first, though. So before we print this, whatever random minimum value that this received should be printed on the first one, and then be printed not be printed on the second one because it's deleted. But we've got to. Oh well. In order. Oh, that's why. There we go. Is that going to work? What was it? What was in order? Oh, we got to give it a. This should probably be private because we have to give it a current. But if hackishly here, I can go ahead and give it the t.root. There we go. This should work at least for testing. None type object is not okay. Well, there it is. Nodes is going to have a first element, isn't it? Oh, the list is equal to this. And then pass in the list. That's what gets changed. It doesn't actually return anything. And then the list, the first one there, I can go ahead and delete it. That's not working. Darn it. At least it's running, though. So delete.
Something happened,
Say what?
something happened on the last one. On the
Oh.
last one we tried, you already did it.
Okay. All right, I'm crossing my fingers here and thinking that the issue was it was too slow to save. I mean, I'm using VS Code in a browser here. That last change that I made, it probably took like 2 seconds or something to actually save and persist to the server, and now it's actually running. Yeah, it's maybe not. Oh, whoa. Yep, there we go. I've got some problems here. Well, no, actually that makes sense. What if the first random thing that you put in is the minimum, right? It's not. I was thinking balanced binary search trees here. It could be that I ended up deleting that root, right? And I'm not. Actually, there's also a bug here too, right? If I want to delete the root, it's not simply just deleting the entire tree here, right? That's bad, right? To do fix this. We were doing so well. We got 90% of our assignment done in only 50 minutes. You're not assigned this, by the way, but this would be like an assignment maybe in computer science 2 that would take 2 weeks or something, and we did it in 50 minutes. I'm not expecting to do 2 weeks assignment in 50 minutes without bugs. All right. That's just a quick review of trees. When we come back on Monday, we'll actually use them for an application, Huffman coding, which is a compression algorithm. Yeah.